Okay, good afternoon, everyone. I'm Dongjin from UC San Diego. And today I'm going to talking about efficient latent link recommendation in sign networks. This is a joint work with David A. Meyer and Dacheng. And in this presentation, I will first introduce the background and motivation of our study, and then I will briefly introduce the generalized AUC and derive two of its lower bounds. And then I will show how to develop two different latent link recommendation algorithm based upon these two lower bounds, and then I will show the experiment results and draw conclusions. Okay, so what is side networks? In side networks, the relationship between between user and the item could be positive or negative, indicating relationships such as trust or distrust, like or dislike, and friends or foes. And in the left figure, we can see it's a side social network. In real world applications, there will be Wikipedia, Slashdot, or opinions are all this type of networks. And on the right hand side, it's a side bipartite network, and YouTube is a network like this. And so what's the difference between the side network and on-site network? In on-site network, the relationship between user item is whether there exists a link between them or not. So the link recommendation problem in on-site network is that we aim to suggest each user a list of people or items that with whom this user might create new connections to. And so in order to perform link recommendation in on-site networks, many approaches has been developed. And that can be categorized into two types. One is the explicit network topological feature-based approaches, including like common neighbors, dynamic case, supervised random works, and so on. And the other is the latent feature-based approaches, including point-wise methods, pairwise methods, and list-wise methods. Note that pairwise methods and list-wise methods are based upon some sort of ranking loss. And also, many approaches can be used for on-site network to conduct link recommendation. But in side networks, the problem is a little different because we have three types of possible cases, which is the positive link, negative link, and the unknown status link. And so in order to perform link recommendation in side network, we have to make an assumption, which is that we assume that the user behavior analytics in side network is that the more extreme the positive and the negative links will be reviewed before less extreme the ones. So based on this assumption that the link recommendation problem in side network can be cast into, we aim to produce a ranking list such as personalized ranking list such that we can rank positive links on top of the ranking list and negative links at the bottom of the ranking list and unknown status link in between. And we are hoping that for the unknown status links, there were some of them are relative positive, some of them are relative negative. So some of them will be, the relative positive one will be ranked relative on top, and the relative negative one will be ranked relative at the bottom of the rank list. That's our goal. So in order to solve this problem, there were two difficulties. One is that the traditional ranking measures like AUC, MAP, and NDCG may not suitable to quantify such a ranking list, including positive, negative, and unknown status link. AUC, obviously, because it's focused on binary ranking. MAP and NDCG can somehow be used to mirror a ranking list like this, but keep in mind that in real-world application, we often have a lot of unknown status links in between. So in this case, MAP and NDCG may focus on evaluating the top-ranked positive links, and when when you try to evaluate the links at the bottom, negative links at the bottom of the ranking list, it may not be sensitive to quantify such a ranking list very well. And another issue is that how to perform link recommendation inside network effectively and efficiently. So in order to do so, we introduce a generalized AUC, which is assuming X is a partially observed side network. Then given a ranking list for user I, we assume that the P denotes the observed, P denotes the set of the observed positive links, and N denotes the set of observed negative links, and O denotes the set of the unknown status links. And given this definition, we can define the GAUC as shown in this formula. The first in the parenthesis, the first term here actually quantifies the ratio of the positive links which were ranked above all the non-positive links. And here the second term actually quantifies all the negative links which were ranked below the non-negative links. So the GAUC is actually basically a linear combination of these two terms. And but with GAUC there were two problems. One is that it actually because it's based on pairwise comparison, it does not explicitly emphasize that the positive links should be ranked on top, and all the negative links were ranked as the bottom of the ranking list. So, and another issue that keep in mind that here is based upon pairwise comparison. So when the number of P and the number of O union N is relatively similar, then the computation of this mirror may be an issue, especially when we handle with bigger networks. So, so we derive two lower bounds of GAUC to solve this problem. Here's the lower bound 1 for GAUC. It's very simple. It's just based upon the principle that arithmetic mean is larger than or equal to the geometric mean. And in the first term here, we can see this basically claims that given each of the positive link, it should this term is 1 if and only if it is about all the non-positive links. The similar case for any negative links. It should be below all the non-negative links. And we can actually simplify this lower bound by comparing only to the maximum of this set and the maximum of the non-negative set. So actually, this lower bound 1 actually quantifies the number of positive and negative links which were ranked as the perfect position, the ratio of the since it only quantifies the number of the ratio of them, and we can derive a more strict bound to make all the positive links were ranked as the top, and all the negative link was ranked as the bottom. That's what happens here. It basically claims that this term holds if and only if all the positive links were ranked above all the non-positive links, and we can also simplify it as we did for the lower bound 1, and then this term only holds when the minimal ranking score of the positive set is larger than the largest ranking score of the non-positive set. Similar case for the negative set, not negative links, the set of negative links. And here we give a comparison of AUC, GAUC, lower bound 1 and lower bound 2, assuming that on left is the top of the ranking list and the right is the bottom of the ranking list, and plus is the positive link and minus the negative link. Then for the row 1, we can see that all the positive links are on top, all the negative links are at the bottom, so all of them are 1. For the row 3 and row 4, there were no positive link on top, no negative link at the bottom. So both the lower bound 1 and lower bound 2 are 0. And for this case, we can see that only one positive link was on top. So the lower bound 1 actually counts the ratio of how many positive and negative links were on top or at the bottom. But bound 2 is 0 because there were one positive link which were not on top. So this is basically how that works. And in order to perform link recommendation, we use a low rank model to encode the ranking score, and also we use a log likelihood of the sigmoid function to approximate the indicator functions for lower bound 1 and the lower bound 2 here. So here is the objective for the first link recommendation algorithm we proposed. It's basically optimize the lower bound 1, and the first term encodes the first term of lower bound 1, and second term encodes the second term of lower bound 1, and these two are regularization terms to prevent the model from overfitting. And in order to optimize this objective, we can, in each iteration, we random sample a subset of positive and negative links, and a subset of unknown status links. Then for each positive link, instead of using the maximum ranking score, because only using one of the maximum or minimum ranking score here may be unreliable. So we consider, in practical application, we actually use the mean of a number of the largest ranking score in the non-positive or non-negative sets to estimate the gradient and do gradient update. We keep updating this. Then we do then we update U, and we iteratively, and then repeat this procedure until the objective converges. Then, so for similar thing happen for the ELR2, which is our second link recommendation algorithm, which basically optimizes the lower bound 2. And these two terms basically is a approximation for the indicator function in the lower bound 2, and these two are other regularization parameters. So the optimization procedure is quite similar with the first algorithm. The only difference that we need also to replace the maximum ranking score in N or the minimum ranking score in P with the mean of the several largest ranking score N or the several of the smallest ranking score in P, which will make the gradient be relatively stable. So we evaluate the effectiveness of these two proposed link recommendation algorithms with 4 different data sets. Here are the detailed statistics of this data sets. And for link recommendation, we use GAUC, AUC, and mean average precision to evaluate them. And to evaluate the performance of the top K link recommendation, we use the precision at the top K and record top K for the positive and the negative links. So here's the performance of the link recommendation, and maybe a little blur here. Keep in mind that the solid red line here represents the optimizing the GAUC with hinge loss, and the dashed line here, dashed black line here, is the first algorithm we used, and the solid black line is the second algorithm we developed. As you can notice that for the GAUC, the first algorithm we proposed actually performed better than the other. This is mainly because it's a lower bound of GAUC. At the same time, the second algorithm, the objective of the second objective is trying to optimize the lower bound 2, which is too loose compared to the GAUC. But for the AUC over the positive and negative links and the MAP also positive and negative links, we can see that the second approach basically consistently outperforms the other approaches. This is mainly because it put more emphasis on ranking the positive link on top and negative link at the bottom. So we also evaluate these two approaches based for top K link recommendation. And as we can see here, our proposed approach consistently outperform baseline approaches here. And here's the precision. The top one is precision at top K, and the bottom one is recall at top K for the over the four different data sets. And we also evaluated the efficiency of our proposed algorithm by comparing it with baseline approaches over the movie length data set when 16% of the observed entries were used for training. And then we can see that our approach actually used less time to achieve convergence. And here we study the parameter sensitivity of the two proposed approaches. The top one is for the first approach with the three different criteria we used. And the second one is the second approach we proposed for these three different criteria. As we can see, here is the low rank. Here's the rank of the low rank. And here's the hyperparameters. We set the two hyperparameters equally for simplicity here. And as we can see, when R is larger than 10 and the lambda is larger than 5, all these two algorithms, the performance of these two algorithms were relatively stable. So that's our conclusion here. We derived the two lower bounds for GAUC, which can be computed in linear time. And we developed two efficient latent link recommendations algorithm to infer a personalized ranking list of latent links by optimizing the two lower bounds we developed. And then we compared the two proposed approaches with top performed baseline approaches over the four benchmark data sets. Our experiment results indicate that our proposed approaches were both efficient and effective. Okay, that's all. Thanks.
So if you ignore the signs,
yes.
What would this formulation boil down to? So for example, in the input data you have these positive and negative signs.
Yes.
And we just utilize them simply saying there is a connection. And then what would happen to the formula if you do that? That means if you ignore the sign.
If I know the sign or
No, if you ignore it.
ignore the sign. Yeah, sure. Okay. So the question is that if I ignore the sign, what will happen for the algorithm? It can actually be used to perform link recommendation in on-site networks.
Okay. The follow-up question is that now you consider the sign as well.
Yes.
Is the prediction better or worse in terms of just the connection?
I didn't compare to the. Oh, sorry. So the question is that when we have the signs and compared to on-site case, what's the performance of the algorithm? Sorry, I didn't have compared this algorithm, but that's a good point. I think I should do that to see whether there's some interesting thing. Yeah. Any other question?